Okay, so good morning. Is it still morning? No, afternoon. And welcome. So let's have a quick show of hands here. So who has had a chance to play with an Arduino in the past? Okay, good. So fair number of people. Who's tried using the Galileo? One person. Okay, interesting. Does anybody here work for Intel? Nobody. Okay. That may be a good thing. When I put this session together, I thought to myself, okay, the Galileo board is from Intel. So it's kind of like the Raspberry Pi, but it has some differences. And one of the big differences is the fact that you can plug in these Arduino shields to it. And I thought to myself, this could be an interesting presentation to do in terms of looking at how we could use Java and talk to the Arduino shields and therefore do some interesting things from a sort of Internet of Things interfacing sort of perspective. And so this is really the story of my journey in trying to make this work. And it has proved to be a challenge, as we'll see as we go through the slides. There are a number of things about the board which have made it quite challenging to actually get things to work. And I was very happy when yesterday afternoon, about 2 o'clock, I actually got the demo that I was trying to get working. So I thought, great, I actually have something to show people beyond a blinking LED. So hopefully that's going to work. We'll see. Right, so in terms of the agenda, I've broken out. So we'll talk a little bit about the basics of the Arduino. I realize a fair number of people here have already used the Arduino, but it's worth spending a few minutes just talking about what the Arduino is and some of the details about its architecture. And that will become very relevant when we start talking about the Galileo, because we'll do the same thing. We'll talk about what the Galileo is and how the architecture of that works and the big differences. Then I'll talk a little bit about Zulu Java on the Galileo, because I work for Azul, and one of the things we've done is we ported the OpenJDK to the Galileo. So we've basically done a build of the OpenJDK that runs on the Galileo and using the various architecture and support that it has on the board. And we've done a couple of other things because we've also done a port of the device IO API. And again, I'll kind of talk about that as we go through. And then most of what I'm going to talk about is how we can actually do some Java Arduino interfacing. This was really the sort of goal that I had when I started doing this presentation, was to think, right, I want to be able to use Arduino shields with Java so that I can use all that interesting sort of interfacing type capabilities that they have, but also use the power of Java, the fact that there's lots of useful libraries available, the fact that there's all these kind of frameworks that we could take advantage of and do some interesting things. So that's what we'll spend most of the time talking about. And then a few conclusions at the end and where we might go next. So the basics of the Arduino then. Arduino's been around for quite a while, and it really was the sort of a board which came out several years before the Raspberry Pi. And the Raspberry Pi, as I'm sure you all know, has become very popular. Lots of them have been sold, and they've become a very popular board for makers and people trying to develop projects using embedded types of capabilities. But the Arduino has been around for quite a while before that and allows you to do a lot of the things that you can do with Raspberry Pi. In fact, it allows you to do some things you can't do with the Raspberry Pi, specifically the ability to have analog inputs. So yes, with the Raspberry Pi, you can have analog inputs, but you've got to have a separate board that allows you to do that. Arduino just gives it to you as part of the default way of doing things. If we look at the architecture of the Arduino, what you've got at the core of this is the Atmel 80 mega microcontroller, not a CPU, it's an MCU. So it's a microcontroller. And then there's a whole range of things that sort of sit below that in terms of interfacing. You've got an EEPROM, there's serial I/O capabilities, there's digital pins that you can connect to it, there's analog pins, as I mentioned, you've got the ability to use timers, you've got interrupts, you can access the RAM, and there's also flash I/O on there as well. So that's all the kind of hardware side of things. Then, in terms of software, there's an AVR GCC runtime and libraries. So there's a compiler that will allow you actually to compile code. There's a set of runtime libraries that are provided by default, and then there are additional user libraries which are made available when you have a shield. So if the shield needs specific capabilities in terms of communication, like it uses I2C or SPI, and so you need to have an interface to that, there'll be a library that somebody will create which makes it simpler, gives you a set of methods that you can call in your application and control the different features of the board. And then the thing that really sits on top of that is the Arduino Sketch. And for those of you who've already used the Arduino, you'll be familiar with this. But Sketch is really just an IDE that was written in Java and allows you to have the capability of controlling the Arduino. Really, what you do there is two things. You create a setup function and you have a loop function. So the setup allows you to do things that you want to do, funnily enough, as setup. And then the loop is what you're going to do continuously when the application runs. And you take that, you use the IDE, you compile the sketch, which uses the GCC underneath, compiles it into native microcontroller code, downloads it onto the Arduino, stores it in Flash, and then when you boot it up, it'll run your sketch. So that's the kind of like fundamentals of the kind of software architecture. If you look at the top of the Arduino, it has a well-defined layout. So this is the sort of Arduino Uno type of board. There's a whole variety of these boards. This is kind of like the most common, I suppose you would say. And the pins are laid out in a specific way, obviously, so that you've got a standard, which means if people are creating a shield to go on that, they know how big the board is, so they know the dimensions. You can separate the pins by a certain amount, and then you know which pins do which function, and then obviously you can use that in terms of interfacing between the shield and the Arduino. So you'll see that essentially what we've got is there are 6 analog pins at the bottom there. A couple of those also can be used for I2C communication. Then on the top row, you've got 14 GPIO pins, so these are digital ones. A couple of those can be used as a UART for serial communication, and 3 of those can also be used for SPI. So if you need that kind of communication, all those things are supported. Then there's a few other pins which are the basic sort of 5 volt, 3.3 volt ground pins and so on. So that's what we're kind of working with in terms of the board layout. If you look at the kind of internal architecture, it's actually really quite simple. This might not look simple, but it is. So what you've got is the 80 mega chip in the middle, and it has a whole bunch of connectors on it, a whole bunch of pins. And it's very simple to wire those to the connectors on the board, which kind of makes sense, really, because that's the way it was designed. So you've got a number of pins which can be used as analog input. They can also be used as digital input. You've got a whole bunch of pins that can be used as digital inputs. The same ones can be used as SPI. They can be used as I2C. And it's all controllable within the microcontroller itself. So from a board construction point of view, you just simply wire the pins on the microcontroller to the connectors on the board, and it's as easy as that. So we'll see why this is very important in a few minutes. So then, as I said, you get a whole bunch of different shields that you can get. So there's things like you can do Ethernet shields if you want to connect to a network. There's a relay shield for controlling things that are outside of sort of 5 volts. Maybe you want more current. There's also a similar sort of thing for controlling motors. There's ones for having LCD displays. You can get OLED displays as well. All sorts of things like GPS, GPRS, joystick, even one for CAN bus. So if you want to connect the Arduino to your car, you could do that as well. So there's lots of different shields available. And many of them use I2C or SPI because there's more data that needs to be transferred in a more complex way. So you can't simply connect a number of the GPIO pins or the analog pins. You have to actually have data that's being transferred across a bus, and so you use I2C or SPI. Right, so let's have a look now at the Intel Galileo. Now, the Intel Galileo is a more complex board. doesn't use a microcontroller. It actually has an Intel Quark system on a chip X1000. So this runs at 400 megahertz, and it's basically equivalent to the old 32-bit Pentium. For those of you who can remember the Pentium processor, then that's essentially what you've got here. It's a shrink-down version of the Pentium. It is single-core, single-threaded, so there's no ability to do things really in parallel. But obviously, if you're using an operating system that can simulate that through the idea of time sharing, then you can do that using the operating system. It has 256 megabytes of RAM, which means you can actually run a full operating system in terms of Linux on it. It's got 8 megabytes of flash, which actually can contain a bootable image. So if you want to store something when you actually boot it up, it can do that. Alternatively, there's a micro SD slot on there. You can put a bigger version of the operating system on that, and then you can boot from the SD card rather than flash. That's much more like the Raspberry Pi kind of way of doing things. It also has a nice little PCIe slot underneath, and that will allow you to connect something like a Wi-Fi card to it, so you can get Wi-Fi through that. It has USB 2. According to the documentation, there are 3 USB 2 connectors on here. I can only find 2. Apparently there's 3. It also has a little header for TTL UART, so you can connect the sort of serial cable to that, which is what I've done here, and that will allow you to see the boot messages, so you don't have to wait for it to boot up before you connect on the network. You can actually see the boot messages coming up on the screen. And obviously it has the Arduino compatible expansion pins, so they're laid out in the same way, the same size, so you can plug a shield in if you want. Architecture. Now this is where things get a bit more complicated, because the Quark is much more of a general purpose CPU. It's not a microcontroller. So unlike the Atmel MCU, it doesn't have as many GPIO pins. It doesn't have as many I/O pins that you can just connect to directly. So you end up with this much more complex looking diagram in terms of the way things are organized. So there's a couple of things on there which are reasonably simple. It has an ADC chip, which supports the idea of analog to digital. It's a 12-bit resolution. The Arduino only does 10-bit resolution, so that's nice. That's controlled through an SPI interface from the Quark. Then there's an I2C that connects to various multiplexers. Now, multiplexers allow you to take the same set of pins and share them so that you can configure a smaller number of pins to be able to do different things. And that is really where things get interesting, as we'll see as we go through some of the actual explanation of what's going on. So you've got multiplexers, you've also got GPIO expansion chips, which allow you to, again, increase the number of GPIO pins available so that you can have the same layout for your shield. So you've got the 6 analog pins, and then you've got the, 14 I/O pins as well. So all of those are supported, but you've got this much more complex architecture in terms of the way that it's dealt with from the hardware. From a compatibility point of view, it's basically the same as the UNO R3, so the Rev 3 board, which is, again, a very common type of board, so you can get these in lots of different places. And what they've done is they've allowed people to use the board. You can plug in the shields, and so long as the shields are supported on the UNO R3, then they should, in theory, work on the Galileo. The way that works is that Intel have taken the core Arduino libraries and they've recompiled them for the Quark processor. So all of the things like the TTY UART, the digital pins, the I2C, the interrupt handling, all of those libraries have been recompiled and made available so that you can take your sketch, compile it rather than using the AVR GCC, you use the Galileo GCC, which is essentially just GCC, build a Pentium version of the code, put it on the Galileo, and off it'll go. Now, they've actually tested various shields, and they've done some sort of certification of various shields. So there's a bit.ly link there that I've done, and you can see what they've actually tested and what they've verified as working. Now, if you want to use an Arduino Shield, in addition to having ported the libraries, Intel also provides you with a version of the Arduino IDE. It's pretty much identical to the ordinary IDE, it just has support for the Galileo board, so you can select it from the board that you want in terms of what you're compiling for, and it also supports the specific download for the Galileo. So there's a little bit more complexity in terms of downloading it onto the Galileo compared to an Arduino. So the way that works, you write your sketch, you compile it. When you download it to the Galileo, rather than it being stored in the flash of the microcontroller, it puts it into the /sketch directory, and it creates a sketch.elf executable. When the machine boots up, it will look, there's a process that looks in the sketch directory. If it finds a sketch.elf, it executes it. And it's essentially just a binary executable. The only thing that you have to do if you want to run it directly is to put /dev/pts/0 on the end. So it redirects the output from that to a particular place. The problem with this that I see is that it's a bit limited in terms of application development. If you wanted to do real-world development of IoT type things, you're not really going to do it from the Arduino IDE. You're going to want to use either native code or Java, and you want to sort of do more things than you could simply do with a sketch. And the other thing is, you see, if you're just going to use a sketch, why wouldn't you just use an Arduino? Because it's a whole lot cheaper. But anyway, so that's the way that it works in terms of the Galileo at the moment. Now, if we look briefly at Zulu Java on the Galileo, essentially what we do at Azul is we do JVMs. So we have two product lines that we have. One is Zing, which is our commercial low latency JVM, and then we have Zulu, which is a build of the OpenJDK. Now we do that for desktop systems, so you can get it for Windows, you can get it for Mac, you can get it for Linux. But we also have sort of projects that we're working on in terms of porting it to embedded systems. And we've got a number of customers and clients that we're working with on that. So we take the OpenJDK source code, we do some necessary porting, and make sure that the code actually runs on the board that we're working with, and then we run the TCK on it. So we guarantee that it actually passes all the TCK tests, and so it is proper Java. You have got exactly the same as you would have if you downloaded it from anybody else who says it's Java. So in terms of this bit of the project, it was actually pretty simple. This was the simple bit of the project, was you take the JRE, take the downloadable bundle, put it onto the Galileo, and you run it. So you just run Java. Well, almost. This is where we start getting into the fun bits, because I have to say that almost every part of this project was a struggle. So you almost can run Java. So what you have to be careful of is that there are a couple of different SD card images that Intel make available. One of them is called the IoT Dev Kit, and that's the one you want to use. Because if you use the IoT Dev Kit, it provides all the libraries you need, and you can take Java, you drop it in there, you run it, and it works. There's another one called the SD card 1.0.4. Now, who wants to guess which one I used first? Yes, the one that doesn't work. SD card 1.0.4. Now, this has some weird library stuff in it, in that there's a lot of libraries which you would expect to be there, which aren't there. So when you try to run Java, it doesn't work. And this is where you get into the fun bits of some of the Linux things. Now, I've been tweeting about some of this stuff, and Steve, who's sitting in the back there, he said to me, "You're becoming a real grumpy old man on Twitter." And it's true, because there's so many of these things, and I'm like, it doesn't work, and it's like, oh, this should be different. And one of the things that really annoyed me was when I ran Java on this. And so I typed ./Java -version, thinking, okay, let's just make sure the JVM starts up. And what I get back is ./Java, no such file or directory. I'm thinking, it's there, I can see it. So I do ls, there it is. I do file, it's an executable. I run it again, I still get no such file or directory. And I'm like, but it's there, why are you telling me there's no such file or directory? So I think about this a bit, and suddenly I'm watching TV, and it's like, light bulb moment. It's missing a library, isn't it? It's actually the library which is the thing that it can't find. So if you do LDD on Java, you'll find that it lists out the libraries it's looking for, and you'll find that some of them are missing. So that took me a while to figure that out. And then after a bit of consultation with various people, they said, oh, no, you want to use the IoT dev kit. Switch to the IoT dev kit, suddenly Java works, and we're back in business. So Java is running. OK, so now let's talk about Java-Arduino interfacing, because now the fun begins. So my goal was reasonably straightforward. I wanted to use Java to control some Arduino shields from the Galileo, so that we could take some Java code, we could interface with the hardware, we could use libraries, we could communicate over the network, we do all sorts of interesting things. Okay. Now, in order to do that, I figured there were several parts that were required. One was we needed the Galileo board set up correctly. Next part was probably going to need some sort of cross-compiler for native code, because we're going to have to do some native code here at some point. Then, once we've got some native code that we can compile, we need to write a Java library. Java library is probably going to use JNI, but there are other ways of doing things, so we'll see how that goes. And then when we've got some sort of library, we'll write an application that does something, and we can actually see what's going on. Great. So, Galileo board setup. We've already talked about this a bit. So the first thing is to use the IoT dev kit SD card image. Don't use the other one. Now, this is a distro. It's a Linux distro, but it does have some challenges. Again, it's like one of these things where everything is a bit of a struggle. So there's no standard FTP client on here. So you can't just do FTP blah. No. You have to do FTP get or FTP put. And that involves extra typing, not just because you've got to type get or put, but also you've got to type username and stuff like that and password and things like that. So it's just a bit fiddly. And then if you want to start up an FTP server, because I thought, right, rather than doing FTP from the Galileo to my other machine, I'll do the other way around. So I found there was an FTP server, but it's this kind of very memorable command, TCP svd 0 FTP FTPD -w ampersand. And then you get an FTP client set up. OK. And the other thing was VI. Who uses VI? OK, who uses Emacs? Oh, OK, we were more of a VI audience. Good. I'm a VI user. And so I wanted to use VI to edit some files on the machine. And then you find things like, you're typing away and you make a mistake. So you go, U, and you get a message. U is not implemented. It's like, come on, U is not implemented. And then you type dot, because you want to repeat the command, and it doesn't do the same thing as you did on the previous command. So eventually I gave up with that, and I figured, right, I'll use VI on a different box, and then FTP the file across to the box. OK. And then, as I say, installing the Zulu runtime, that was actually the easy bit once we got past the fact that we didn't need to use the other SD card image. Cross-compiler for native code. So my first attempt at this was I found that Intel actually provide you with a cross-compilation environment that you could put on a Linux box. I thought, great. So I installed it on my Ubuntu Linux box, and I ran the install script, and the install script didn't work. So I was like, oh, OK. So I had a look at it, tried to do a bit of debugging, and eventually I looked at it and I thought, no, this is just, it's a bit messy. It's taking too much time. I won't do it that way. So then I thought, right, OK, well, the Galileo is reasonably powerful. Let's put the compiler on the Galileo. So I tried that. Installed the compiler on the Galileo board. Install script didn't work. So again, spent a few minutes fiddling about with it, trying to figure out why the files weren't in the right place and why things didn't work. And I thought, no, that's still not working. So third attempt, I discovered that Intel provide you with a very nice IoT dev kit VirtualBox image. And that did work. So I installed that on my got it on my laptop, and I could get that working, except that you don't choose the default kernel. If you choose the default kernel, it doesn't actually work. So you have to choose the third one on the list, which is specifically for the 486 architecture, and then it boots up, and you can actually run the compiler. As you can see, everything was a struggle. So we got to the point now where I've got a cross-compiler where I can actually do something. Great. OK. So then I started thinking about how do I actually do the interfacing to the shield. And I thought, well, there are really 4 ways you could approach this. The best way for me was to say, okay, let's use a JNI interface. Let's take the Arduino libraries and put a Java wrapper around them. So in effect, we could take what we're writing in a sketch, and because it kind of looks like Java anyway in many ways, let's use the same method names and use it from Java. So we'll write a wrapper around that, and we can do that. Great. Because the other thing about that is nice is that for the libraries which people provide for other shields, most of them are open source. So if we can do that for the standard Arduino libraries, we can probably do it for the libraries that support different shields. So we'll be able to make a nice extensible framework, and it would all kind of work. So that was the first idea I had. Second thing, I thought, well, okay, if we don't do that, what other things could we do? And one of the things you can do is you can use this device IO API. And we'll talk more about this later on. This was still quite a clean solution, I thought, because it's a standard Java library that's available, and it allows you to talk to things like GPIO pins and analog inputs and things like that, and I2C. So it'd still be fairly clean, but not quite as compatible, because for the other libraries that people were providing for shields, we probably wouldn't be able to work with those in quite the same way. Third solution was native file system access to the I/O, because the way that Intel have implemented all this is, if you look at the way it works underneath, it all goes through file system. So all of the GPIO pins are represented by a file within the file system, and you either write to it or read from it and do things with it that way. So I thought, okay, well, that's kind of like a third option. It's not quite so clean because we're having to work with all this file system stuff. And again, it's not so compatible because we might have issues with libraries and so on. And then the fourth option, which I haven't actually bothered to explore, was having a native I/O process where we could essentially write a sketch, which would act as a sort of proxy. And we would have a native application that we could use Java, communicate with, and say, okay, give me the result of what's on the analog pin, tell me what it is, or send this value to the digital pin, and so on. So not a very clean solution. I call it the dirty solution, and certainly with some potential performance impacts, because if you're sending messages back and forth between these two processes, it's clearly not going to be quite as good as if you're just running one process. So let's look at the first option, my exploration of trying to interact with the Arduino libraries. So who here has used JNI in the past? Ooh, reasonable number of people. Keep your hand up if you like JNI. Oh, somebody does. One person. So JNI is one of those things that's been around for a long, long time. And there is talk of actually rewriting it. JDK 10 may have a new version of JNI. And I remember when I worked at Sun many years ago, talking to one of the engineers about JNI, and I said, JNI is really fiddly, isn't it? And he said, oh yes, we designed it that way. It's like, okay, great. That's exactly the design process you want to take, is to make it fiddly. But he said, it's designed to discourage people from doing it, because we want people to use Java on its own. It's like, okay, still not quite seeing the logic of that, but anyway. So the idea of JNI, for those of you who haven't used JNI, is to allow you to access C or C++ functions or methods from a Java application. And as I said, it's not really difficult. It's just a bit fiddly. What you have to do is you have to add some native method definitions to your Java code to say these are the methods that I want to use, which are going to be supplied by the native code. Then you run a thing called Java-H, generate some header files. Then you write some C or C++ code to implement those JNI functions. And then you compile it into a shared library. And then you can use that with your application code. But you have to make sure that you get the configuration right. And this is the thing I always find a bit fiddly, is making sure that you get the java.native path right and getting the LD library path right, if you're using Linux, obviously. So if we look at some example of this. So here's what I was trying to do. I wanted to access a digital pin. And there are two methods that you use in your sketch, which are called pin mode and digital write. So I thought, right, I'll just create two methods in my Java library with exactly the same name. And then I'll use native methods, which I'll call things slightly different to avoid confusion, especially with the compiler. And I'll have wire pin mode and wire digital write, because they're part of the wire library. So in our code, all we're doing is we're saying when you call pin mode, you simply call the native method wire pin mode with the same variable. So it's not very complicated code. It is literally just a wrapper. What we then do is we create a header file. So you run Java-H with -d where you want the headers to go, -jni because you want to know it's jni, set the class path of where you're going to get the Java code from, and tell it which particular class you want to generate headers for. And you'll get something looking like this. So JNI export void, JNI call, and then you get a very long name which explicitly states what the particular method is you're trying to create. And then you get some values that get passed to it as JNI env, JObject, and a couple of integers. So there's a mapping between the native types and the Java types. And obviously we've got the same thing for our other call. What you then do is you write some native code. So you basically cut and paste, because it just takes too long to type. So you cut and paste from the header file, change the values, so you actually add variables to the types that are defined there. So you've got the environment, you've got the object, pin, and mode. And then you put in the native code that you actually want to execute, which in this case is just calling the pin mode method with pin and mode. So again, it's sort of going from pin mode in Java land through wiring pin mode, which is the kind of native interface, to call pin mode in the native libraries. Compile that using -shared, -fpic, -o, generate a .so file, specify where the header files are going to come from, and your .c file. And you end up with a .so file. Great. So now, assuming that we've compiled everything correctly and we've done everything, we can execute our Java application. So I thought, right, simplest application, I will use one GPIO pin, I will put an LED on it, and I will turn it on and off. I will blink the LED. So I run it. Java -d, java.native.path, say where my native code was coming from. -jar, blink.jar. Anybody want to guess what happened? No. Not so fast. So I ran it, and what did I see? I saw my underbar Z4 init IPPC undefined. Okay. So I looked at that and I thought, right, okay, something's missing. So I have a look around, and I do some nm, and I grep, and I find that there is a variant.cpp file. And this kind of makes sense, because there's actually the core libraries. And what I did was I used the IDE, and I found there was a build directory where there was a core.a file, which was most of the libraries that were being used. So I basically unpacked the archive and then rebuilt it as a .so file. But then I found that there's also this variant.cpp, which is a file that's specific to the board that you're using. So different Arduinos, different Galileo boards. Found this variant.cpp, which was a variant.o file, and then added that to the library. So that error went away. Great. Now I get underbar Z4 setup v, underbar Z4 loop v undefined. So again, nm, grep, and I find, okay, this is located in main.cpp. That makes sense, because this is essentially the entry point for the sketch. You remember I said in the sketch, you have a setup method and you have a loop method. So this is where you would put these things when you write your sketch. So they'd be provided by the sketch. So I figure, okay, well, we're not writing a sketch, so we don't actually need these. So I just took those out, and lo and behold, that error went away. Ran it again. Underbar Z, DLPV undefined. nm, grep, oh dear, not located anywhere. Okay, so where do I go from here? So then I thought, right, can we fix it? Bob the Builder. So now I started learning about things like mangled references. In C++, because you can have overloading of methods, you can have methods with the same name but different parameters. So the way that the compiler deals with this is it mangles the method name into something which is unique based on the types of the parameters that are being passed. So that's where you get these underbar Z whatevers. And there's this little utility which comes as part of the GCC code, which allows you to look at it and unmangle the references. So you can run C++ filt on that, and you'll get what is ZDL PV. It turns out it's the delete method in the TTY UART code. So I thought, oh, okay, right. So there's a missing delete. I'm not a C++ programmer, so I'm like, delete. Okay, right, okay. So I thought, right, let's just delete TTY UART from the library and see where we go from there. Unfortunately, it's one of these things where you kind of find cyclic references or references to references, and it just gets all too complicated. So it's like, oh, that's not going to work. Then I thought to myself, well, hang on. The compiled Arduino sketch works. So somewhere, the Arduino sketch is getting the delete in TTY UART. Where's it getting it from? So strace is available on the Galileo. So then I strace the executable for the sketch.elf to find out what's going on and look at all the libraries it's opening. And I find, oh, okay, there's a lib32 and a user lib32 directory, which it's getting some libraries from. So it's like, aha, right. What can I do there? So I try setting LD library path to include lib32 and user lib32, thinking this will solve the problem. No, because what actually happens is the JVM won't even start now. The JVM is using those libraries, and it says, oh, it's actually in the pthread library, it says, no, there's a missing version there, so it won't start up. Okay, right, so then I go back and I say, okay, well, I can explicitly load the libraries using system.load in my code. So I do things like system.load, lib32, lib.so.0. And there's 6 libraries that I need to load. Okay, the order is important because you've got the dependency of one library on another, so you have to load them in the right order, but then you find there's cyclic dependencies between them, and that gets really complicated and doesn't work. And then the JVM crashes, even with not setting the LD library path. And even with that, I still couldn't resolve delete. So I'm like, okay, this is about last week, this was. I was getting very despondent at this point. So then I thought, right, let's compile TTY UART with an empty delete method. No. Okay, so I found the sources for it, but there's no make file. And then I thought, okay, I'm not writing a make file for this. It's just too complicated. So the answer is, no, we can't. So at this point, I gave up on JNI. I decided this just wasn't going to work. So let's look at what did work. So I did have some experiments and some demos. So let's see where I went from there. Like I say, the first thing that I actually wanted to do, the simplest form of demo that I could think of, was der Blinkenlichten. Now, anybody, for those of you who are old enough, there's this kind of like sign that used to be put up in computer rooms, because they used to be called computer rooms rather than data centers. And it was like, genickt Gefingerpocken. It's all about like, not poking your finger in the computer and stuff like that. Anybody recognize the machine at the bottom there? Oh, PDP-8, very good, because you can just read it on there, but you could definitely not read it from there. PDP-8, first big machine I ever saw with blinking lights on it. So I thought, right, okay, I want to do this. I want to blink an LED. That's got to be the minimum in terms of a demo. So I thought, right, I'll use the device IO library and do that. So this is simpler. And the problem is a couple of things that we have to get around. One is that the device IO library is designed to work with a range of boards. So the pin numbers don't necessarily map one-to-one with the pin numbers that you have on your board. So it took me a while to find how this worked, but eventually I found that pin 13 on the Galileo maps to pin 7 in DIO. Then the other thing that you need to get around is the security policy, because if you look at the Java DIO API, originally it was designed for Java ME. And then what's happened is that there is a project in OpenJDK. Azul are heavily involved in this in terms of porting it to different architectures as part of Java SE. So we've done a Java SE port for device IO on the Galileo. It does have a very fine-grained, and I will say complex, security policy permissions way of setting things up. So if you want to blink an LED, you need a policy file which has something like this in it. So you have to grant permission on the GPIO pin permissions, and then there's this weird thing with colons and the number of the pin, which I never did quite understand, but it's kind of like make files, somebody wrote the first make file, and then everybody copied it and modified it for themselves. So it's the same thing with the permissions file here. Everybody takes the first one and then just modifies it. So there's a couple of GPIO pin permissions that you need, and then device management permission as well to open the pin. The alternative, as I discovered, is that you can just use grant permission java.security all permissions, and then that just gives you permission for everything, which is necessarily a good or a bad thing. So to use this, what we do is we simply set the property for the policy to point at that file. Could do that from the command line, but we did it in static method or static code. And then we need to set up the pin for using it. So we use the GPIO pin config. There's a builder that we can create for that. And then you set the pin number. You tell it what direction the pin's going to go in, because you've got input and you've got output. And then you need to set the drive mode, which is one of these things that you need to start looking into the complexity of electronics at this point. So you set it for output push-pull, and then you build it, and then you can use that pin, and you can set its value either to high or low, or on or off, which is basically a Boolean. Then you can write a simple loop, and you go, I want to flash my LED a certain number of times, and great. So in theory, that should work. So then all we have to do is run the code. So we just do java -jar blinker.dio.jar. And because the DIO library is installed as part of the JDK, it goes in the lib directory, then it should run. So, except it doesn't work. So at this point, I'm really getting despondent, because it was like, it doesn't work. Why doesn't it work? I mean, everything, I followed all the instructions, I followed everything I found on the web, and believe me, I Googled everything. It still didn't work. So why didn't it work? Unless you run the Arduino sketch first. So something that's happening in the Arduino sketch is setting up the pins correctly to whatever you need to do. So it's like, okay, that's really weird, but anyway, so that works. Okay. So it's something to do with the way that the multiplexing of the GPIO pins works. Because as we'll see in a moment, there's actually a bit more that we need to understand about that. Now, I was going to show you a demo, but I'm running a bit short on time. So for the sake of getting to the other demo, which is a bit more interesting, I won't show you an LED flashing, because I'm guessing you've probably seen that before. So the other thing that I thought, right, okay, I'm going to use a shield. I want to do something that will actually show something realistic. So I found this particular shield in my collection of shields, which is an electromyocardiogram shield. And so it's got a number of leads that connect to it. And then you connect those, and I'm actually wearing the little devices, so I'll wire myself up in a moment. So you've got one on your left wrist, one on your right wrist, and one on your right ankle. What it does is it simply measures the voltages of the sensors, and it also measures the difference in voltages between the 2 points, and obviously you've got 3 points. So the idea is that you've got 6 different values, the 3 voltages and then the 3 differences. It's a nice, simple interface. So it doesn't rely on any I2C or SPI or anything like that. It's just 6 analog to digital channels coming in. So if you can read those 6 analog to digital channels, you can get the information. Great. So again, nothing is ever simple with this. So I had to dig through the wiring analog.c code and find the multiplexing selection of the analog table, which then led me to some other definitions. And eventually I found that if you look at the different pins, what you're looking for is GPIO pin 48, 50, 52, 54, 56, and 58. Great. So that's part of the puzzle. But then you need to set these up. So this is part of this multiplexing game. So what you've got to do is, first of all, you've got to export the pin to be able to use it. So you echo 48 to GPIO export. Then you have to tell it that you need it to go in the output direction. But hang on, we're reading from the input direction, aren't we? So why are we setting it to be an output direction? Aha. Set it to be an output, and then you write 0 to it to tell it that it's going to be used as an analog input. That's kind of like in Windows, where you click on Start to shut your computer down. But anyway. So then, again, this should work, but it doesn't. So I wrote a little sketch which literally just read data from the 6 analog lines, ran that sketch, and that did all the setup for me. There's some other magic there that I'm missing, and then I could do it. I could actually get it to work. So reading the data, okay. So if you want to read the data, rather than using the GPIO pin directly, you have to go through a different thing, which is sysbus IIO, devices, IIO device 0, and then there's a bunch of files there, which are the raw voltages or a scaled voltage. So you can go to IN underbar voltage 0 raw, and if you cat that, it gives you the current reading as a 12-bit value on that pin. Great. So you want to just read that from the file system. But of course, this being the Arduino, this being the Galileo, it's not simple. Because it's designed as a file, but you try and read from it, you can't read from it multiple times. Because something in the way it works, it doesn't allow you to read from it multiple times. So you've literally got to close the file and open the file again every time you want to read from it. Now, the board actually runs at 256 hertz. So 6 analog pins, 256 hertz. That means you're opening and closing files 6 times 256 times a second. It does actually work, but it doesn't seem like the most efficient way of doing things to me. And when I S-trace the Arduino libraries, they don't do that. So I'm not sure how the Arduino libraries do that yet. Maybe I'll find out at some point. So demo setup, very simple. I used the Galileo board. I had the Java server process, where it's just reading the values, made it available across TCP/IP. Then I wrote a little JavaFX client that ran on my laptop and displayed the values coming from there. Now, I'm actually going to save the demo to the end because it'll save me having to come back to my slides. So I'll do that in a moment. So I've got 5 minutes left. That should be all right. So conclusions. Right. If I was going to go further with this, I'm really not sure I am. Simplify the Java code, figure out how all this sysfs thing works, and actually make the whole library simpler. Do some things with I2C, do some things with SPI. That would be interesting because there's obviously more interesting shields that you can use if you want to go with those. Galileo as a development board. Well, first of all, it's more expensive than a Raspberry Pi. It's actually about twice the cost. I would describe it as harder to work with than the Raspberry Pi. I think from what I've shown you in the last sort of 45 minutes, I think you'd agree with me that it's harder to work with than the Raspberry Pi. The advantage is it does support the Arduino shields directly. And it does have built-in analog to digital converters, so those are kind of like a nice plus if you want to do that. And it is useful if the target hardware you're working on is Intel-based rather than ARM-based. Zulu embedded Java, as I said, certified OpenJDK build, ported for the Intel application architecture. Also, we have a port available now for ARM32, so it works on the Raspberry Pi. We've done the port of the device IO API, and as I say, Arduino control, not simple. Use support of the DIO, low-level control. Looking at the GPIO pins is definitely something that's going to need more work. Resources, I won't bother leaving this up, but I've done a couple of bit.ly links you'll be able to get from the slides. I'll post them on SlideShare later on, and you'll be able to see things there. So what I'm going to do is I'm going to try and run the demo now, which will be interesting. So first thing is, first thing I'll have to change the, oh no, must remember a couple, okay. All right, let me see if I can change the screen so that you can see it as well. Displays, arrangement, mirror. Oh, okay, good. Right, that works. Oh, that is a very small, even I can't read that. It's on my screen. Right, it's not going to work. No. Goodness me. Oh, that's better. Yeah, I can actually read that now. Okay, so I have logged into the Galileo. And so what I need to do is I need to go to the sketch. And Right, so this should blink an LED, hopefully. Nope. Oh dear. Ah, now I know what the problem is. Okay, we'll try this. I'm not sure if it's going to work. Okay, so I'm going to do... Turn my Wi-Fi off. Okay, right, so that's listening on there. So now if I wire myself up, hopefully, no, should put that the other way around. Right, if I don't lose the Galileo in the process. Now what I should be able to do, hang on. Okay, good. That bit's working. So theoretically, this is a big theoretically here. If I run this application, oh yes, it does work. Okay, look. So you're actually seeing data that's being read from the Galileo. Now, at the moment, I would assume that you probably think that my heart is suffering from some very severe trauma. So one of the things that I've actually figured with this is that the data I'm reading is not like a simple signal which shows my heartbeat. I think that I have to do some interpreting of several of the values together and actually merge them to actually get the result. But hopefully that gives you an idea that you can actually read some information and actually then get something working. Like I say, I got that working yesterday afternoon. I was very happy when I got something running, and I could actually see some values coming through. So, yeah, I hope that you've enjoyed this. If you've got questions, I don't know how long the break is now, whether we've got, no, we've only got 10 minutes. But if you've got questions, please feel free to come up and talk to me afterwards. Thank you very much.